Hi, welcome to Chapter 9, Overview Part 6, where we're going to talk about covalent bonding, hybrid orbitals, and multiple bonds. So the first thing we're going to discuss is review a little bit. We discussed this a couple videos ago. How does a covalent bond form? With respect to electron orbitals, how do bonds form? So you see here you have two hydrogens, and when they are far apart from each other, there is no attraction. As you bring them together, you start to get some overlap of their electron orbitals. And the electron in the opposite atom starts to get attracted to the nucleus in the opposite atom. And then you keep pushing them together and you reach your maximum attraction, which would be right here, your minimum potential energy. And this would be your bond length. If you try to push them even closer together, you're going to get significant overlap. And now the two nuclei come too close to each other, and you get proton repulsions here. Okay? So initially, there is no attractions. As you get closer, the electron in one atom is attracted to the nucleus of the other, and vice versa, until you reach the optimum distance that balances the repulsions of the nucleus and the attractions of the electrons to the nucleus. But then as you try to push them even closer together, the two nuclei start to repel each other. In this diagram, how many electrons are coming from each orbital? And the answer is 1 electron from each orbital to make one bond where you share 2 electrons. So, just to review again what we said on the previous slide, an increased overlapping begins as the atoms come together until you reach a balance where the like charge repulsions and the electron nucleus attraction kind of balance each other out. Your atoms can't get too close because then the nucleus, the protons of the nucleus start to repel each other. And that's why you see this great increase in energy here. Increased overlap brings the electrons and nuclei closer together while simultaneously decreasing the electron-electron repulsions. And then again, however, if the atoms get too close, the internuclear or the proton repulsions greatly raises the energy. That is in a nutshell, how a covalent bond is formed. Now, what if you compared a single bond to a double bond to a triple bond? So let's look at this diagram over here. What do you notice is the difference between this? Well, first of all, which bond is the strongest? And how would you know that on this graph? Well, we know that the triple bond is the strongest. And if you look here, it has the lowest potential energy. So the straight line is the triple bond, then comes the double bond, then comes the single bond. Which bond is the shortest? Well, look at the distance here. It is also the triple bond. So as you have more bonds, you can actually get your two nuclei closer to each other before the protons start to repel. So what happens when we are mixing these atomic and molecular orbitals? When atoms share electrons to form a bond, their atomic orbitals will mix to form molecular bonds. In order for these orbitals to mix, they must have similar energies, they must overlap, and they must be close together. So here's an example. As you're bringing them together, they're overlapping, they have similar energies, they're close enough together, you get this overlapping and you form a covalent bond. So valence bond theory. In this theory, electrons of two atoms begin to occupy the same space. This is called an overlapping orbital. So here you have overlapping. This is an overlapping orbital. this is between hydrogen, and each hydrogen electron is in the 1s. So you have 1s over here, 1s over here overlapping. Now we're bonding with hydrogen, which ends in 1s1, and chlorine, which ends with 3p5. So the S, remember, is a sphere, and the P looks like a peanut. And when they come together, you have this overlapping again. And here we have a bond between the 3p5 of each. Remember, the P looks like a peanut, so they have two of them overlapping. And that overlapping will lead to the electron sharing and forming a bond. So one of the criteria to form this bond is that the electrons have to have similar energy. So first of all, you use VSEPR to predict the shapes of your molecules. But how does that fit with orbitals? Well, let's use methane as an example. So you want to draw your best Lewis structure for methane. This is a typo. And it becomes tetrahedral. If you look at carbon, its electron configuration is 1s2, 2s2, 2p2. So if it shares the 4 electrons, it's 4 valence electrons, it needs to share in order to form 4 bonds, each one going to hydrogen. So if your electrons are in the s and the p orbitals, they actually have different energies. And we said that when we're forming our bonds, they kind of have to have the same energies. We want 4 equal energy bonds. Like one of these bonds doesn't have different energy from this bond. They all have the same energy. So if they all have the same energy, we need 4 electrons in carbon to have the same energy. But 2 of the electrons are in the 2s and 2 are in the 2p. The 2s is lower energy than the 2p. So how do we make these 4 electrons have the same energy so we could form 4 equal energy bonds? Well, we have to do something called hybridized orbitals, okay? So if we look at carbon, in methane, carbon needs to form 4 equal energy bonds. Here is our orbital notation of carbon. So if we're going to form 4 bonds using this, you put 1 electron in here, then 3 down, okay? But you can't, we have to use these 4 electrons, and these 2 are lower energy than this one. And hydrogen is not really a big deal because hydrogen is only 1 electron, and that's its orbital diagram. Okay, so remember your S looks like a sphere and the P look like peanuts, so we're going to use these long skinny balloons to kind of represent that. And when you're forming bonds, you are using your valence electrons. So how do we get 4 equal energy electrons from carbon? Well, so just a reminder, the S orbital and the P orbital have different energies. And in carbon, we need to make 4 equal energy bonds. So therefore, we need to average the electrons in the S and the P. So we end up with 4 equal energy electrons, which are ready to bond. When you average orbitals, that is called hybridization. Okay? Hybridization is the averaging of orbitals. And since in this case, we need to make 4 bonds off of the carbon, we need 4 equal energy orbitals. So in order to do that, we have to average 1s and all 3 p's. So this is called sp3, 1s and all 3 p's. Another way to be able to identify your hybridization, that's what this is called, hybridization, is the number of orbitals you hybridize has to equal your domains. So remember, in methane, we have 4 domains. So if you add, we have 1s and 3 p's together, visualize that there's a little superscript here, but there isn't. But if you add them up, that equals 4. Okay. Now notice how these hybridized orbitals look. We took an s and a p. Actually 3 p's, right? And we averaged them together. So this little s here kind of combined with this, and it makes your hybridized orbital. So this is kind of how I draw it. If I wanted to get my sp3, I need 4 of these. That's how they look now. So they went from this to this. So here's another way of showing it. We're mixing an S with a P, and we end up with this kind of small lobe and a large lobe. Okay? So if we just had SP hybridized, we are averaging 1S and 1P. Right? Because if you add up the superscripts, it equals 2. This is when you have 2 domains. And if you tie 2 of these together, you're going to make this shape here, which is linear. And isn't that what we get when we have 2 domains, linear? If we have our sp3, so we tie those 4 balloons together, we're going to make tetrahedral. And this is how you get your shapes. Okay? So if you connect the 4 hybridized orbitals together, you will form the tetrahedral shape as shown below. So how do we get this again? So here are carbons, valence. These are carbon, valence electrons. We have to get my 2 S's and my 2 P's to all have the same energy. So if I was drawing this kind of like a Aufbau diagram, the 2P is higher energy than the 2S. And I need to average all 4 of these to make my 4 equal energy orbitals. So I'm going to draw them in the middle. So they are higher energy than the S, but lower energy than the P. And now I have 4 electrons that I could put in here. So look at that. I have 4 unpaired electrons ready to make 4 bonds. 4 unpaired electrons ready to make 4 bonds. And, so these are sp3, they are all the same energy, which is what we need, because one bond to hydrogen was not more energetic than the other. Okay? And what do these sp3 looks like? Well, remember the S looked like a sphere, the P looks like a peanut. When we merge them, it's like a little sphere with this lobey thing. And if I tie 4 of these together, it kind of looks like the tetrahedral. Okay? So that's carbon. And maybe I could draw that a little bit better. So what does carbon look like? So here you have so this is carbon. And in methane, I have carbon bonded to hydrogen. Hydrogen is a 1s1. Right? And that is a sphere. So the hydrogen is a sphere. I'll do them in green. So that's each hydrogen. And what do we have here? We have 4 overlapping bonds forming. These 4 overlapping bonds are called sigma bonds. And we use the Greek sigma to represent that. So here is, in balloon form, our methane, okay? And if we needed to kind of label this, the carbon are the white balloons, and the green balloons are your hydrogens. And this shape is tetrahedral, and its hybridization is sp3. So how do you know your hybridizations? Well, once you know your domains, you can figure out your hybridization state. So if you have 2 domains, you are averaging 1s and 1p. If you have 3 domains, you are averaging an s and 2 p's. 4 domains, which we did previously, you're averaging 1s and 3 p's. What happens when you get to 5 domains? Well, we can't have any more p's because the p orbital only has 3. But what comes after the p? Do you remember? D. So it would be sp3d. What if you have 6 domains? It would be sp3d2. Remember, all of these superscripts have to add up to your number of domains. Once you can count your domains, you could find your hybridization and you could find your shape. So those domains are very useful. So the type of bonds. So we mentioned a sigma bond, but there is something else called a pi bond. Okay? So when we have a single bond, all single bonds are sigma bonds. Okay? Now in a double bond, let's take oxygen for example. You have a sigma and you have a pi bond. So in double bonds you have one sigma and one pi. A triple bond, let's take nitrogen, you have two pi bonds and a sigma bond. So one sigma and two pi's. So you always have to have at least one sigma, but then everything else is a pi. What is the difference between a sigma and a pi bond? So remember, sigma bonds we showed before is when you have head-to-head overlapping. Head-to-head overlapping, right here. This is a sigma bond. This is a sigma bond. This is a sigma bond. Head-to-head overlapping. Okay? And their symmetry, or their electron density, is about, it goes around the internucleus axis. So right here. It's, if you draw that like that. Okay? Now the pi bond is not head-to-head overlapping, it's side-to-side overlapping. So here is your internuclear axis, and the overlapping is occurring above and below it. Above and below it. Okay, and this is your pi bond. Another nice way to see it. This head-to-head overlapping is your sigma bond. This overlapping above and below is your pi bond. So remember, single bonds are always sigma bonds because sigma overlap is greater and it's resulting in a stronger bond and more energy lowering. So your first bond is always going to be a sigma bond. In multiple bonds, one of the bonds is a sigma and the rest are pi. So in this case, you have a sigma and a pi. Here you have 2 pi and 1 sigma. So how does this look when you actually look at a molecule? So here we have H2CO. Okay, remember your H bonding electron is in the 1s. And that looks like a circle. Oops. And that's what's happening right here. See this blue circle here? That's your hydrogen. Now, how many domains does carbon have here? 3 domains. So that would be sp2 hybridization. So that means you're tying 3 of these lobes together. And that gives you trigonal planar. Look here. You see how you have 3 purple lobes? And they're all on the same plane? This is the plane, this rectangle. That is trigonal planar. So here is carbon. And on the ends of each of these, you have your hydrogen overlapping, making sigma bonds. Okay? Now here you have oxygen. How many domains does oxygen have? 1, 2, 3. So this also has 3 domains. So that will also make a trigonal planar. And here you have head-to-head overlapping for your sigma bond. In these lobes here, you have your lone pairs. So this is oxygen, this is carbon. Maybe I'll color them so we know. So here's hydrogen. And this is our carbon. And oxygen, I'll make purple. Okay, so what are we missing? We are missing our double bond. We are missing the pi bond, which I will make green. So we are missing the pi bond. So if I look at my electron configuration for carbon, so I have 2s, 2p, and how many orbitals do I have to hybridize for this case? Only 3 of them. So I have to hybridize 3 of these, and I will make 3 sp2s. Then there is a p that was not hybridized that I could leave out. And I have to put 4 electrons in these, following Hund's rule, okay? So that's carbon. Oxygen ends in, hold on, let me erase this here. Oxygen ends in 2s, 2p, 4. And in this case, we said there's 3 domains, so we need to hybridize 3 of these, right? So that gives me sp2 and 1 unhybridized p. And I have to put 2, 4, 6 electrons in there. So 1, 2, 3, 4, 5, 6. These 2 are paired up. Those are my lone pairs. This single one here bonds with my carbon, and that's what happens right here. That's the bond that you see there. Now I have a P from oxygen and a P from carbon that are not hybridized. So they still look like the skinny peanuts. So we are going to do that in green. So we kind of put the squiggly here to show that they are overlapping above and below. So this is our orbital drawing for this here. And if you want to see how the book does it here, this is your pi bond. Okay, this is sigma, sigma, sigma. So in this case, you have 3 sigmas and 1 pi. Here are your lone pairs. Okay, here is it in balloons, and this is going to help you with your balloon lab a little bit. But this is for oxygen. So oxygen looks like this. So 3 domains each. So here are your sp2s, sp2s. You have 2 lone pairs in each of these. You have a sigma bond, and here is your pi bond. What happens if you have a triple bond? Okay, if you have a triple bond, you end up with 2 pi bonds. So you see the red one here, and the bluey purple one here is another pi bond. And this is kind of how your book draws it too. Now remember, the p orbitals are at 90 degrees to each other on the x, y, and z. So we talked about localized and delocalized electrons when we were talking about resonance. And it kind of happens in this too, okay? You're bonding electrons in your pi or sigma that are specifically shared between 2 atoms are called localized. So if you have them and they just stay within that one bond, it's called localized. But what happens when we have resonance? Okay, then we get our delocalized electrons. So if we look at nitrate here we have this double bond that's kind of rotating around. There are 3 domains here, so it's sp2 hybridized. So remember, 3 domains look like that. Trigonal planar. So if you look here are your 3 domains. So, and you have your oxygens coming off here. If we go back, see your oxygen with some lone pairs on them. Okay, so in reality, each of the 4 atoms in the nitrate ion has a p orbital. The p orbitals on all three oxygens overlap with the p orbital of the center hydrogen. So this is our delocalized. So your electron can jump around in there, and that's how your double bond moves. So this kind of helps us understand resonance a little bit better. It's not like it's distinctly here. They're all kind of merged together so that double bond could move. This means that the pi electrons are not localized between nitrogen and one of the oxygens, but rather delocalized throughout the whole ion, so they're able to jump around. Okay, so here is our benzene again. So here you had your alternating pi bonds. So they kind of just show it. That's what the circle here means, okay? Here are your pi bonds that are delocalized. And that is the end of this chapter.